What if the universe we see today is just a tiny fragment of something far grander? Picture this. In the blink of an eye, the entire cosmos expanded faster than the speed of light, stretching from something smaller than an atom to the vast expanse we know today. This is the cosmic inflation era, a moment in time so brief yet so profound that it holds the keys to understanding everything around us. But here's the twist: despite decades of research, this era is shrouded in mysteries that even the brightest minds can't fully explain. Why did inflation start? What triggered it? And could there be other universes out there, hidden beyond our reach? These questions don't just fascinate scientists, they challenge the very way we think about reality. In this video, we're diving deep into 25 of the most mind-bending mysteries of the cosmic inflation era. From the strange uniformity of the universe to the elusive inflated field that might have powered it all, we'll explore the theories, the controversies, and the unanswered questions that keep astronomers and physicists up at night. So, if you're ready to unravel the secrets of the early universe and discover why this tiny fraction of a second changed everything, stick around. By the end of this journey, you'll see the cosmos in a whole new light. Let's begin. Now, let's take a closer look at the very beginning of this cosmic story, the origin of cosmic inflation. To understand why scientists even proposed this idea, we need to rewind to the early days of the Big Bang theory. While the Big Bang model explained a lot about the universe's expansion, it had some puzzling gaps. For instance, why does the universe look so uniform in every direction? And why is its geometry so perfectly flat? These questions led physicists to propose a radical solution: cosmic inflation. Imagine the universe just a fraction of a second after its birth, undergoing an exponential growth spurt. In less time than it takes to blink, it expanded faster than the speed of light, smoothing out irregularities and setting the stage for the cosmos we see today. This rapid expansion wasn't just a wild idea, it solved some of the Big Bang's biggest problems. It explained why distant regions of the universe, which should never have been in contact, look so similar. It also accounted for the universe's flatness, a feature that seemed too precise to be a coincidence. But here's where it gets even more fascinating. This explosive growth wasn't random, it was driven by a mysterious energy field, often called the inflated field. Think of it as a cosmic engine, pushing the universe to stretch and grow at an unimaginable rate. And while we don't yet know exactly what this field is or how it worked, its effects are written all over the universe, from the distribution of galaxies to the faint echoes of the Big Bang in the cosmic microwave background. Inflation left its fingerprints everywhere. So, what does this mean for the structure of the cosmos? Well, without inflation, the universe as we know it might not exist. It's the reason we have galaxies, stars, and planets instead of a chaotic, uneven mess. But as much as inflation answers, it also raises new questions. What triggered this rapid expansion, and what was the universe like before it began? These are the mysteries we'll keep exploring as we dive deeper into the cosmic inflation era. Next up, we'll tackle one of the most intriguing puzzles of all, the horizon problem, and how inflation might hold the key to solving it. Now, let's shift our focus to one of the most puzzling questions in cosmology, the horizon problem. Picture this: when we look out into the universe, no matter which direction we choose, the temperature of the cosmic microwave background radiation is almost exactly the same. This might not sound like a big deal at first, but here's the catch. These regions of space are so far apart that, according to the speed of light, they should never have been in contact with each other. So how did they end up being so uniform? It's like walking into two different rooms on opposite sides of the world and finding them set to the exact same temperature, even though no one ever communicated between them. This is where cosmic inflation comes in. During that brief but explosive period of rapid expansion, the universe stretched so quickly that regions that were once close together were suddenly flung far apart. Before inflation, these regions were close enough to exchange heat and reach a uniform temperature. Then, as the universe expanded, they were carried away from each other, but the uniformity remained. It's as if you blew up a balloon with a perfectly even pattern. No matter how much you stretch it, the pattern stays the same. Inflation, in this sense, acts like a cosmic iron, smoothing out the wrinkles and creating the uniformity we observe today. But here's the mystery that still baffles scientists. Why was the universe so uniform to begin with? What set the stage for inflation to work its magic? Some theories suggest that the universe started in a state of thermal equilibrium, but that just pushes the question further back. Others propose that the inflaton field, the mysterious energy driving inflation, might have played a role in creating this uniformity. Yet, despite these ideas, we still don't have a complete answer. The horizon problem remains one of the most compelling reasons to believe in cosmic inflation, but it also reminds us how much we still have to learn about the early universe. As we move forward, we'll explore another fascinating puzzle, the flatness problem, and how inflation might explain why the universe's geometry is so perfectly balanced. Stay with us as we continue unraveling the mysteries of the cosmic inflation era. Now, let's turn our attention to another cosmic puzzle that has left scientists scratching their heads: the flatness problem. Imagine the universe as a giant sheet of paper. If you were to measure its geometry, you'd find that it's almost perfectly flat, not curved, not warped, but flat. This might seem like a minor detail, but it's actually a huge mystery. Why? Because the universe's flatness is a sign that its density is incredibly finely tuned. If the density were even slightly higher, the universe would have collapsed in on itself long ago. If it were slightly lower, everything would have flown apart so quickly that galaxies and stars could never have formed. So how did we end up with a universe that's just right? This is where cosmic inflation steps in to offer an explanation. During that rapid expansion phase, the universe stretched so much that any curvature it might have had was smoothed out, like stretching a crumpled piece of paper until it becomes flat. Inflation essentially ironed out the universe, leaving it with the near-perfect flatness we observe today. It's a bit like blowing up a balloon. The larger it gets, the flatter any small bumps or wrinkles appear. But here's the catch. For inflation to work this way, the universe's density had to be incredibly precise from the very beginning. If it were even a tiny bit off, the universe wouldn't be flat, and we wouldn't be here to observe it. This raises a deeper question. Why was the universe's density so finely tuned in the first place? Some scientists argue that this fine-tuning is evidence of a multiverse, a vast collection of universes, each with different properties. In this scenario, we just happen to live in the one where the density was just right for life to exist. Others suggest that there might be some underlying principle or law of physics that we haven't discovered yet, one that naturally leads to this precise balance. The flatness problem doesn't just challenge our understanding of the universe's geometry. It forces us to ask fundamental questions about why the cosmos is the way it is. As we continue our journey through the mysteries of the cosmic inflation era, we'll dive into another intriguing question: the monopole problem, and how inflation might explain the absence of these elusive particles. Stay with us as we keep unraveling the secrets of the early universe. Now, let's shift our focus to another fascinating mystery tied to the cosmic inflation era: the monopole problem. Picture this: according to grand unified theories which aim to merge the fundamental forces of nature, the early universe should have been teeming with magnetic monopoles. These are hypothetical particles that carry a single magnetic charge, either a north or a south pole, unlike the magnets we're familiar with, which always come with both. But here's the twist: despite decades of searching, scientists have never found a single magnetic monopole. So, where did they all go? This is where cosmic inflation comes to the rescue. During that rapid expansion phase, the universe stretched so dramatically that any magnetic monopoles that might have formed were diluted to the point of being virtually undetectable. Think of it like dropping a handful of salt into a bathtub versus dropping it into the ocean. In the bathtub, you'd still notice the salt, but in the vastness of the ocean, it becomes almost impossible to find. Inflation effectively spread out the monopoles, making their density so low that they're nearly impossible to detect in our observable universe. But this explanation doesn't completely solve the mystery. While inflation accounts for why we don't see monopoles today, it doesn't explain why they were so rare in the first place. According to grand unified theories, monopoles should have been produced in abundance during the early universe. Their absence challenges our understanding of particle physics and raises questions about whether these theories need to be revised. Could there be something missing in our current models? Or is there a deeper principle at play that we haven't yet uncovered? The monopole problem isn't just about missing particles, it's a window into the fundamental laws that govern our universe. It forces us to question whether our theories are complete and whether we're missing a crucial piece of the puzzle. As we continue to explore the mysteries of the cosmic inflation era, we'll delve into another mind-bending idea, the multiverse theory, and how it might explain some of the strange features of our universe. Stay with us as we keep peeling back the layers of cosmic history. Now, let's venture into one of the most mind-bending ideas tied to cosmic inflation, the multiverse theory. Imagine this: what if our universe isn't the only one out there? What if cosmic inflation didn't just create the universe we know, but countless others, each with its own unique set of physical laws? This is the heart of the multiverse theory, and it's a concept that challenges everything we think we know about reality. Here's how it works. During cosmic inflation, the universe expanded at an unimaginable rate, stretching space itself. But what if this expansion didn't happen uniformly everywhere? Some theories suggest that different regions of space could have stopped inflating at different times, creating bubbles of space that each became their own separate universe. These bubble universes could have entirely different properties, different constants, different forces, even different dimensions. In one universe, gravity might be stronger, while in another, the speed of light could be slower. The possibilities are endless, but here's the catch: if these other universes exist, how could we ever know? By definition, they're beyond our observable universe, separated by vast stretches of space and possibly even different physical laws. This raises a profound mystery. Is it even possible to observe or prove the existence of other universes? Some scientists suggest that if two bubble universes collided, the impact might leave a detectable mark in the cosmic microwave background, the afterglow of the Big Bang. Others propose that gravitational waves from such collisions could provide clues, but so far no definitive evidence has been found. The multiverse theory isn't just a wild idea, it's a potential solution to some of the biggest mysteries in physics. For example, why does our universe seem so finely tuned for life? If there are countless universes with different laws, it's not surprising that at least one of them would have the right conditions for life to exist. But this also raises questions about the nature of science itself. If we can't observe or test other universes, does the multiverse theory fall outside the realm of science? Or is it a glimpse into a deeper truth about reality that we're only beginning to understand? As we ponder these questions, we're reminded that the mysteries of cosmic inflation are far from solved. The multiverse theory challenges us to think bigger, to imagine a reality far beyond what we can see. And as we continue our journey through the cosmic inflation era, we'll explore another intriguing mystery: the role of quantum fluctuations in shaping the universe as we know it. Stay with us as we unravel more of the cosmos' deepest secrets. Now, let's turn our attention to another fascinating piece of the cosmic inflation puzzle: quantum fluctuations. These tiny, random variations in energy might seem insignificant at first glance, but they played a monumental role in shaping the universe as we know it. During the rapid expansion of cosmic inflation, quantum fluctuations were stretched across vast distances, leaving behind a faint imprint on the fabric of space itself. These imprints became the seeds for the large-scale structure of the universe: galaxies, galaxy clusters, and even the cosmic web that connects them all. But how did something so small lead to something so enormous? Here's the mystery: quantum fluctuations are inherently random, yet they somehow gave rise to the organized, intricate structures we see today. Imagine tossing a handful of sand into the air and watching it form a perfectly symmetrical pattern as it falls. That's the kind of cosmic magic we're talking about. During inflation, these tiny ripples in energy were amplified by the rapid expansion, creating regions of slightly higher and lower density. Over billions of years, gravity took over, pulling matter together in the denser regions and eventually forming stars, galaxies, and the vast cosmic structures we observe. What's truly mind-boggling is the scale of this process. The fluctuations that seeded our universe were unimaginably small, on the order of 1 part in 100,000. Yet, these minuscule variations grew into the colossal structures that define the cosmos. This raises a profound question: how did such delicate beginnings lead to such a grand outcome? Scientists are still working to understand the precise mechanisms that allowed these quantum ripples to evolve into the universe's large-scale architecture. One theory suggests that the inflaton field, the energy driving cosmic inflation, interacted with these fluctuations in a way that preserved their patterns as the universe expanded. Another idea points to the role of dark matter, which may have helped amplify these initial seeds into the structures we see today. But despite these theories, the exact process remains one of the great mysteries of cosmic inflation. As we explore this mystery, we're reminded of the delicate balance that shaped our universe. The quantum fluctuations that began as tiny ripples in the early cosmos became the foundation for everything we see: stars, planets, and even life itself. And as we continue our journey through the cosmic inflation era, we'll dive into another intriguing question: how and why did cosmic inflation come to an end? Stay with us as we uncover more of the universe's deepest secrets. Now, let's shift our focus to one of the most puzzling questions about cosmic inflation: how and why did it come to an end? This moment, often referred to as the graceful exit, marks the transition from the rapid expansion of inflation to the hot, dense state of the Big Bang. But what caused this dramatic shift? The answer remains one of the great mysteries of cosmology. One leading theory suggests that the inflaton field, the energy driving inflation, gradually lost its strength as the universe expanded. Think of it like a ball rolling down a hill initially. It moves quickly, but as it reaches the bottom, it slows down and eventually stops. In this case, the inflaton field's energy decayed, causing inflation to end and releasing its stored energy in the form of particles and radiation. This release is what triggered the hot Big Bang, filling the universe with the raw materials for stars, galaxies, and everything we see today. But here's where things get tricky. Scientists still don't fully understand the exact mechanism that caused the inflaton field to decay. Was it a natural process like the ball slowing down, or was there some kind of cosmic trigger that forced inflation to stop? Some theories propose that quantum effects played a role, causing the inflaton field to transition abruptly. Others suggest that the field's energy simply became too diluted to sustain inflation over time. The challenge lies in finding evidence to support these ideas, as the end of inflation occurred in the earliest moments of the universe, leaving behind few observable clues. Another layer of mystery involves the transition itself. How did the universe go from a state of rapid expansion to one of intense heat and density? This process, known as reheating, is thought to have been incredibly rapid, but the details are still unclear. Did it happen uniformly across the universe, or were there regions where inflation ended sooner or later than others? These questions highlight the complexity of understanding this pivotal moment in cosmic history. What makes this mystery even more intriguing is its connection to the larger story of the universe. The end of inflation set the stage for the Big Bang, which in turn gave rise to the cosmos we inhabit today. Without this transition, the universe as we know it might never have existed. Yet, despite its importance, the exact nature of this process remains elusive. As we continue to explore the mysteries of cosmic inflation, the question of how and why it ended stands as a reminder of how much we still have to learn about the early universe. Next, we'll delve into another fascinating aspect of this era, the nature of the inflaton field itself. What is this mysterious energy that drove the universe's rapid expansion, and why has it remained so elusive? Stay with us as we uncover more of the universe's deepest secrets. Now, let's turn our attention to the inflaton field, the mysterious energy that powered the rapid expansion of the universe during cosmic inflation. Imagine this field as an invisible force stretching space itself faster than the speed of light. But what exactly is this field, and why has it remained so elusive to scientists? The inflaton field is a hypothetical concept, meaning it hasn't been directly observed or detected. Yet, it's a cornerstone of our understanding of cosmic inflation. Think of it like the wind. You can't see it, but you can see its effects. In the case of the inflaton field, its effects are written across the cosmos in the form of the universe's large-scale structure and the patterns we see in the cosmic microwave background. But unlike the wind, we don't yet have a way to measure or interact with this field directly. One of the biggest mysteries surrounding the inflaton field is its properties. What kind of energy does it contain? How does it behave? Scientists have proposed that it's a scalar field, meaning it has a single value at every point in space. This simplicity makes it a powerful tool for explaining inflation, but it also raises questions. For instance, why does this field have the specific properties needed to drive such a rapid and uniform expansion? If it's a scalar field, why haven't we found any direct evidence of it in particle physics experiments? Another layer of intrigue comes from the fact that the inflaton field seems to have disappeared after inflation ended. If it was so powerful during the early universe, where did it go? Some theories suggest that the field decayed into the particles and radiation that filled the universe after inflation, but this raises even more questions. How did this decay happen, and why hasn't any remnant of the inflaton field been detected in the modern universe? The challenge of studying the inflaton field lies in its timing. It existed only during the earliest moments of the universe, long before the formation of stars, galaxies, or even atoms. This makes it incredibly difficult to find direct evidence of its existence. Scientists rely on indirect clues, such as the patterns in the cosmic microwave background or the distribution of galaxies, to piece together its story. But without a way to observe the inflaton field directly, many of its secrets remain locked away. What makes this mystery so compelling is its connection to the very fabric of reality. The inflaton field isn't just a theoretical curiosity, it's the key to understanding how the universe began and why it looks the way it does today. Yet, despite its importance, it remains one of the most enigmatic aspects of cosmology. As we continue to explore the mysteries of cosmic inflation, the nature of the inflaton field stands as a reminder of how much we still have to uncover about the early universe. Next, we'll dive into another fascinating question. What triggered cosmic inflation in the first place? What were the initial conditions that set this incredible process in motion? Stay with us as we unravel more of the universe's deepest secrets. Now, let's shift our focus to one of the most profound questions in cosmology. What triggered cosmic inflation in the first place? What were the initial conditions that set this extraordinary process in motion? This mystery takes us back to the very beginning, to a time before inflation, when the universe was in a state we can barely comprehend. To understand the initial conditions of inflation, we need to imagine the universe in its earliest moments. Picture a cosmos that was unimaginably small, dense, and hot, a state often referred to as the Planck epoch. During this time, the laws of physics as we know them break down. Gravity, quantum mechanics, and the other fundamental forces were likely unified into a single, all-encompassing force. But what caused this primordial universe to transition into the rapid expansion we call cosmic inflation? One leading theory suggests that quantum fluctuations played a key role. In the chaotic environment of the early universe, tiny, random fluctuations in energy could have triggered a phase transition, causing the inflattened field to dominate and drive the exponential expansion. Think of it like a snowball rolling down a hill. Once it starts, it grows rapidly and becomes unstoppable. But what set that snowball in motion? Was it a random quantum event, or was there something more fundamental at play? Another intriguing idea is that the universe before inflation was not entirely uniform. Perhaps there were regions of higher energy density that acted as seeds for inflation to begin. These regions could have been the result of earlier processes, such as the collapse of a previous universe or the collision of higher dimensional structures. While these ideas are speculative, they highlight the challenge of understanding the pre-inflationary universe. The problem is that we have no direct evidence of what the universe was like before inflation. The rapid expansion effectively erased any traces of its earlier state, leaving us with only indirect clues. It's like trying to reconstruct the first chapter of a book when all the pages have been torn out. The cosmic microwave background gives us a snapshot of the universe just after inflation, but it doesn't tell us what came before. This mystery is compounded by the fact that our current theories of physics are incomplete when it comes to describing the universe at such extreme conditions. General relativity and quantum mechanics, the two pillars of modern physics, don't work together at the scales and energies of the Planck epoch. To fully understand the initial conditions of inflation, we may need a new theory that unifies these two frameworks, a theory of quantum gravity. The question of what triggered inflation is not just an academic curiosity. It's deeply connected to the nature of reality itself. If we can uncover the initial conditions that set inflation in motion, we might gain insights into the origins of the universe, the nature of time, and even the possibility of other universes. But for now, this remains one of the biggest unknowns in cosmology. As we continue to explore the mysteries of cosmic inflation, the question of its initial conditions reminds us of how much we still have to learn about the universe's earliest moments. Next, we'll turn our attention to another fascinating puzzle, the role of dark energy in the cosmic story. How is it connected to inflation, and what does it tell us about the universe's fate? Stay with us as we dive deeper into the cosmos. Now, let's explore another fascinating piece of the cosmic puzzle, the role of dark energy. This mysterious force, which is driving the accelerated expansion of the universe today, raises intriguing questions about its connection to cosmic inflation. Are these two phenomena related, or are they entirely separate forces shaping the cosmos? To understand this, let's start with what we know about dark energy. Discovered in the late 1990s, dark energy is the name given to the unknown force causing the universe's expansion to speed up. Unlike gravity, which pulls things together, dark energy seems to push space apart. It makes up about 68% of the universe's total energy content, yet we still don't know what it actually is. Some scientists think it might be a property of space itself, often referred to as the cosmological constant, while others propose it could be a dynamic field, similar to the inflattened field that drove cosmic inflation. This brings us to the big question: could dark energy and cosmic inflation be connected? Both involve the rapid expansion of space, but they operate on vastly different scales. Cosmic inflation occurred in the tiniest fraction of a second after the Big Bang. while dark energy has been shaping the universe for billions of years. One theory suggests that dark energy might be a remnant of the inflated field, a kind of leftover energy from the early universe. If this is true, it would mean that the same force that caused inflation is still influencing the cosmos today, albeit in a much weaker form. However, there's a problem with this idea. The energy density of dark energy is incredibly small compared to what we think the inflated field's energy density was during inflation. This huge difference makes it difficult to see how the two could be directly linked. Some researchers propose that dark energy might be a completely separate phenomenon, perhaps arising from a different field or even a new kind of physics we haven't discovered yet. Another possibility is that dark energy and inflation are both manifestations of a deeper, underlying principle. For example, some theories in quantum gravity suggest that the vacuum of space itself has an energy that can change over time. This could mean that both inflation and dark energy are different expressions of the same fundamental process, operating under different conditions. The mystery deepens when we consider the fine-tuning problem. Both inflation and dark energy require incredibly precise values to produce the universe we see today. If the energy density of inflation had been even slightly different, the universe might have collapsed or expanded too quickly to form galaxies. Similarly, if dark energy was stronger or weaker, life as we know it might not have been possible. This raises the question, are these coincidences or is there a deeper connection we're missing? For now, the relationship between dark energy and cosmic inflation remains one of the great unsolved mysteries of cosmology. While we have some tantalizing clues, we lack the definitive evidence needed to piece together the full story. Future observations, such as those from advanced telescopes and gravitational wave detectors, might help us uncover more about these enigmatic forces and how they shape the cosmos. As we continue to unravel the mysteries of the universe, the connection between dark energy and inflation reminds us of how much we still have to learn. Next, we'll turn to another intriguing topic, the BICEP-2 experiment and its controversial claim to have detected gravitational waves from inflation. What does this mean for our understanding of the early universe? Stay with us as we dive deeper into the cosmic story. Now, let's shift our focus to one of the most dramatic moments in modern cosmology, the BICEP-2 experiment and its controversial claim to have detected gravitational waves from the early universe. This discovery, if confirmed, would have been a groundbreaking piece of evidence supporting cosmic inflation. But as we'll see, the story took an unexpected turn, leaving us with more questions than answers. The BICEP-2 experiment, short for Background Imaging of Cosmic Extragalactic Polarization, was designed to study the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. In March 2014, the team announced they had detected a specific pattern in the CMB known as B-mode polarization. This pattern, they claimed, was caused by gravitational waves generated during cosmic inflation. The scientific community and the public were electrified. It seemed like we had finally found the smoking gun for inflation, but here's where things got complicated. Gravitational waves from inflation would leave a unique imprint on the CMB, but so could something else, interstellar dust. Dust particles in our own galaxy can also create B-mode patterns, and distinguishing between the two is incredibly challenging. As other researchers began to scrutinize the BICEP-2 results, doubts started to emerge. Could the signal really be from inflation, or was it just galactic dust? To settle the debate, the BICEP-2 team collaborated with the European Space Agency's Planck satellite, which had mapped the distribution of dust in the Milky Way. The combined analysis revealed that much, if not all, of the B-mode signal detected by BICEP-2 could be explained by dust. The initial excitement gave way to disappointment, and the claim of detecting inflationary gravitational waves was retracted. This episode highlights the immense difficulty of detecting such subtle signals from the early universe. gravitational waves from inflation, if they exist, would be incredibly faint, buried beneath layers of noise and interference. The challenge lies not just in building sensitive instruments, but also in accurately separating the signal from everything else that could mimic it. So, where does this leave us? The Bicep 2 controversy underscores the importance of rigorous verification in science. It also reminds us that the search for answers about the early universe is far from straightforward. While we haven't yet confirmed the existence of primordial gravitational waves, the quest continues. Future experiments like the Simons Observatory and the Lightbird mission aim to improve our ability to detect these elusive signals, bringing us closer to understanding the mysteries of cosmic inflation. As we move forward, the Bicep 2 story serves as both a cautionary tale and a source of inspiration. It shows how science advances through trial, error, and perseverance. Next, we'll explore another fascinating idea: the eternal inflation hypothesis and the possibility that inflation never truly ends in some regions of the universe. What does this mean for the cosmos? Stay with us as we dive deeper into the mysteries of space and time. Now, let's venture into a concept that stretches the boundaries of our imagination: the eternal inflation hypothesis. This idea suggests that cosmic inflation, the rapid expansion of the universe, might not have ended everywhere. Instead, it could still be happening in certain regions, creating an eternally inflating multiverse. Imagine a universe where some pockets continue to expand exponentially, while others settle into the stable, slower expansion we observe today. This raises a profound question: could our universe be just one bubble in an infinite sea of inflating universes? The eternal inflation hypothesis emerged as a way to explain why inflation might not have stopped uniformly. According to this theory, quantum fluctuations during inflation could cause some regions to stop expanding while others keep going. These regions that continue to inflate would give rise to new universes, each with its own set of physical laws and constants. Over time, this process could create an endless multiverse, with countless universes existing side by side, each potentially different from our own. But here's where things get tricky. If eternal inflation is real, how could we ever test it? After all, these other universes would be completely disconnected from ours, making direct observation impossible. Some scientists have proposed indirect methods, such as looking for evidence of collisions between our universe and neighboring ones. These collisions might leave imprints in the cosmic microwave background, the faint afterglow of the Big Bang. However, detecting such signals would require incredibly precise measurements, and so far, no definitive evidence has been found. Another challenge is that the eternal inflation hypothesis relies heavily on quantum mechanics and the behavior of the inflaton field, the hypothetical energy field driving inflation. But we still don't fully understand how these quantum processes work on such vast scales. Without a complete theory of quantum gravity, which unites quantum mechanics with general relativity, testing eternal inflation remains a daunting task. Despite these challenges, the idea of an eternally inflating multiverse continues to captivate scientists and enthusiasts alike. It offers a possible explanation for why our universe has the properties it does, suggesting that we might live in a region where inflation happened to stop, allowing stars, galaxies, and life to form. At the same time, it opens the door to a cosmos far more vast and varied than we can currently comprehend. As we ponder the eternal inflation hypothesis, we're left with a tantalizing mystery. Is our universe just one among many, or is it unique? While we may not have the tools to answer this question yet, the pursuit of understanding drives us forward. Next, we'll explore another intriguing puzzle: the fine-tuning problem, and why the parameters of cosmic inflation seem so perfectly set to create a universe like ours. What does this mean for the nature of reality? Stay with us as we continue to unravel the mysteries of the cosmos. Now, let's turn our attention to one of the most puzzling aspects of cosmic inflation, the fine-tuning problem. This mystery revolves around the fact that the parameters of inflation appear to be exquisitely balanced, almost as if they were carefully calibrated to produce a universe like ours. If these values were even slightly different, the cosmos we know, filled with galaxies, stars, and planets, might never have existed. So why are these numbers so precise? What does this fine-tuning tell us about the nature of our universe? To understand the fine-tuning problem, let's start with the basics. During cosmic inflation, the universe expanded at an astonishing rate, driven by the inflaton field. The behavior of this field, along with other factors like the density of matter and energy, had to fall within an incredibly narrow range of values to allow for the formation of the structures we see today. For example, if the expansion rate had been too fast, matter would have spread out too thinly, preventing galaxies from forming. If it had been too slow, the universe might have collapsed back on itself before stars could even ignite. The balance had to be just right. This raises a profound question. Why do these parameters align so perfectly? Some scientists argue that this fine-tuning is evidence of a deeper principle or law of nature that we have yet to discover. Others suggest that it might point to the existence of a multiverse, where countless universes exist with different parameters, and we just happen to live in one where the conditions are right for life. In this view, our universe isn't special, it's simply one of many possibilities. But the multiverse explanation comes with its own challenges. If there are infinite universes with varying properties, how can we ever test this idea? And even if we could, does it truly solve the fine-tuning problem, or does it just push the mystery one step further? These questions highlight the complexity of the issue and the difficulty of finding definitive answers. Another angle to consider is the role of chance. Could the precise values of inflation's parameters be the result of random fluctuations in the early universe? While this might seem like a simple explanation, the odds of such a perfect alignment occurring by chance are astronomically low. This has led some to speculate that there might be an underlying reason for this precision, one that we have yet to uncover. As we grapple with the fine-tuning problem, we're left with a profound sense of wonder. The universe seems to operate on a razor's edge, with its fundamental constants and laws finely balanced to allow for complexity and life. Whether this points to a deeper cosmic order, the existence of a multiverse, or something entirely beyond our current understanding, the mystery of fine-tuning remains one of the most compelling questions in modern cosmology. With this puzzle in mind, let's move forward to explore another fascinating aspect of cosmic inflation: the missing gravitational waves. Why haven't we found definitive evidence of these primordial ripples, and what could their absence tell us about the early universe? Stay with us as we continue to unravel the mysteries of the cosmos. Now, shifting our focus to another intriguing mystery of cosmic inflation, let's explore the enigma of the missing gravitational waves. These ripples in space-time, predicted to have been generated during the rapid expansion of the early universe, are a key piece of evidence that could confirm the theory of inflation. Yet, despite decades of searching, scientists have not yet found definitive proof of their existence. Why is this the case, and what does it mean for our understanding of the cosmos? To begin, let's revisit what primordial gravitational waves are and why they matter. During cosmic inflation, the universe underwent an exponential expansion, stretching space-time itself. This process would have created ripples, gravitational waves, that carried information about the earliest moments of the universe. Detecting these waves would be like finding a cosmic fingerprint, offering direct evidence of inflation and shedding light on the conditions of the universe just fractions of a second after its birth. So, why haven't we found them yet? One possibility is that the signals are simply too faint. The gravitational waves from inflation would have stretched and weakened over billions of years, making them incredibly difficult to detect with current technology. Another challenge lies in distinguishing these primordial waves from other sources of gravitational waves, such as those produced by colliding black holes or neutron stars. It's like trying to hear a whisper in a crowded room. The background noise can easily drown out the signal we're searching for. Another factor to consider is the scale of inflation itself. If the energy scale of inflation was lower than predicted, the gravitational waves it produced might be too weak for our instruments to detect. This raises the question, could inflation have occurred at a lower energy level, or are we missing something fundamental about the process? Some theories suggest that alternative models of inflation, which don't produce strong gravitational waves, might explain the absence of these signals. But if that's the case, how do we reconcile these models with the other evidence supporting inflation? The search for primordial gravitational waves has also faced setbacks, such as the controversial BICEP 2 results from 2014. Initially hailed as a groundbreaking discovery, the detected signal turned out to be caused by cosmic dust rather than gravitational waves. This incident highlighted the immense challenges of this search and the need for more precise instruments and methods. Despite these hurdles, the quest continues. Future experiments like the next generation of space-based observatories and ground-based detectors aim to push the boundaries of sensitivity and accuracy. These advancements could bring us closer to detecting these elusive waves, or, if they remain undetected, force us to rethink our understanding of cosmic inflation altogether. The mystery of the missing gravitational waves is a reminder of how much we still have to learn about the early universe. Are these waves simply too faint to detect, or do they not exist at all? If they're absent, what does that mean for the theory of inflation? These questions drive scientists to refine their tools and theories, pushing the boundaries of our knowledge. As we ponder this mystery, let's turn our attention to another fascinating aspect of cosmic inflation: the role of quantum gravity. How do theories like string theory attempt to explain the early universe, and what challenges do they face in reconciling quantum mechanics with general relativity? Join us as we continue to unravel the mysteries of the cosmos. Now, let's venture into the realm of quantum gravity, where the rules of the very small meet the vastness of the cosmos. This is where theories like string theory step in, offering a potential bridge between the quantum world and the universe's grand structure. But how do these ideas attempt to explain cosmic inflation? And why is reconciling quantum mechanics with general relativity such a profound mystery? At the heart of this challenge lies a fundamental conflict. Quantum mechanics governs the behavior of particles at the tiniest scales, while general relativity describes the force of gravity and the large-scale structure of spacetime. Both theories are incredibly successful in their own domains, but when it comes to the extreme conditions of the early universe, like those during cosmic inflation, they seem to clash. This is where quantum gravity theories come into play, aiming to unify these two frameworks into a single, coherent picture. String theory, one of the leading candidates for quantum gravity, suggests that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. These strings can oscillate in different ways, giving rise to the various particles and forces we observe. In the context of cosmic inflation, string theory proposes that the inflaton field, the energy field driving inflation, could be connected to these vibrating strings. This connection might explain how inflation began and why it unfolded the way it did. However, the mystery deepens when we consider how to reconcile quantum mechanics with general relativity during inflation. The rapid expansion of the universe would have stretched spacetime to unimaginable scales, while quantum fluctuations at the smallest levels would have played a crucial role in seeding the structure of the cosmos. But how do these quantum effects interact with the large-scale curvature of spacetime described by general relativity? This is a question that still puzzles physicists. One of the biggest hurdles is the lack of experimental evidence. Quantum gravity operates at energy scales far beyond what we can currently probe, making it difficult to test these theories directly. Without observational data, scientists rely on mathematical consistency and theoretical elegance to guide their work. This has led to a variety of approaches, from string theory to loop quantum gravity, each offering a different perspective on how to unite quantum mechanics and general relativity. Another intriguing aspect is the role of extra dimensions. String theory, for instance, requires the existence of additional spatial dimensions beyond the three we experience. These extra dimensions could influence the behavior of the inflatoned field and the dynamics of cosmic inflation. But how do these dimensions manifest, and why are they hidden from our everyday observations? This remains one of the most tantalizing mysteries in the field. As we explore these ideas, it's clear that the role of quantum gravity in cosmic inflation is far from settled. The interplay between the quantum and the cosmic continues to challenge our understanding, pushing scientists to develop new theories and refine existing ones. Could string theory or another quantum gravity framework finally provide the answers we seek? Or will the mystery of reconciling these two pillars of physics persist, driving us to rethink the very nature of reality? With these questions in mind, let's turn our attention to another fascinating puzzle: the strange patterns in the cosmic microwave background. What do these anomalies tell us about the early universe, and could they hint at new physics beyond our current understanding? Join us as we continue to unravel the mysteries of the cosmic inflation era. Now, shifting our gaze to the cosmic microwave background, or CMB, we encounter a treasure trove of clues about the early universe. This faint afterglow of the Big Bang holds imprints of the universe's infancy, offering a snapshot of the cosmos just 380,000 years after its birth. But within this ancient light, scientists have discovered peculiar patterns, anomalies that defy our expectations and challenge the very foundations of our understanding of cosmic inflation. One of the most striking anomalies is the so-called cold spot, a region in the CMB that is significantly cooler than its surroundings. According to the standard model of inflation, such large-scale variations should be extremely rare, almost impossible. Yet there it is, staring back at us from the data. Could this cold spot be a statistical fluke, or does it hint at something deeper? Perhaps a flaw in our theories, or even evidence of a multiverse. Another puzzling feature is the asymmetry in the CMB's temperature distribution. The universe, as we understand it, should be isotropic, meaning it should look the same in all directions. However, the CMB reveals a subtle but noticeable imbalance, with one hemisphere slightly warmer than the other. This axis of evil, as some scientists have dubbed it, raises questions about whether our universe is truly uniform, or if there's something we're missing about the conditions during inflation. Then there's the mystery of the missing large-scale correlations. Inflation predicts that the universe should exhibit certain patterns of temperature fluctuations on the largest scales. Yet, when we examine the CMB, these expected correlations appear weaker than anticipated. This discrepancy has led some researchers to wonder if inflation might not be the full story, or if there's another layer of physics waiting to be uncovered. What makes these anomalies so intriguing is their potential to point toward new physics. Could they be evidence of exotic particles or fields that existed during the early universe? Might they suggest modifications to Einstein's theory of gravity, or even the existence of other universes beyond our own? Each anomaly is like a piece of a cosmic puzzle, challenging us to rethink our assumptions and explore new possibilities. However, interpreting these anomalies is no easy task. The CMB is incredibly subtle, and distinguishing genuine signals from noise requires painstaking precision. Advances in technology, like more sensitive telescopes and sophisticated data analysis techniques, are helping us probe deeper into these mysteries. Yet the question remains, are these anomalies mere quirks of nature, or do they hold the key to unlocking a deeper understanding of the cosmos? As we continue to study the CMB, one thing is certain: these anomalies remind us that the universe is far more complex and mysterious than we often assume. They challenge us to push the boundaries of our knowledge, to question what we think we know, and to remain open to the possibility that the answers we seek might lie beyond the horizon of our current understanding. With these enigmatic patterns in mind, let's turn our attention to another captivating mystery: the possibility that cosmic inflation created primordial black holes. Could these ancient objects hold the key to understanding dark matter, or do they represent yet another cosmic puzzle waiting to be solved? Join us as we delve deeper into the mysteries of the cosmic inflation era. Now, let's venture into a fascinating possibility that ties cosmic inflation to one of the universe's most enigmatic phenomena: primordial black holes. These hypothetical objects, thought to have formed in the earliest moments of the universe, could hold the key to solving one of cosmology's greatest mysteries: dark matter. But how exactly could cosmic inflation have given rise to these ancient black holes? And what might they tell us about the invisible substance that makes up most of the universe's mass? Primordial black holes are unlike the black holes we're familiar with today, which form from the collapse of massive stars. Instead, they are believed to have emerged directly from the extreme conditions of the early universe, during or shortly after the period of cosmic inflation. The idea is that tiny fluctuations in the density of matter during inflation could have created regions so dense that they collapsed under their own gravity, forming black holes. These objects could range in size from as small as an atom to as massive as a star, or even larger. What makes this idea so intriguing is its potential connection to dark matter. Dark matter, as we know, is the invisible substance that makes up about 27% of the universe's total mass and energy. It doesn't emit, absorb, or reflect light, making it detectable only through its gravitational effects. For decades, scientists have searched for dark matter particles, but so far, none have been definitively found. Could primordial black holes be the answer? Some researchers propose that these ancient black holes could account for at least a portion of dark matter. If they exist in large enough numbers, their combined gravitational influence could explain the observed effects of dark matter on galaxies and galaxy clusters. This would be a groundbreaking revelation, linking the earliest moments of the universe to one of its most persistent mysteries. However, the idea is not without its challenges. For one, primordial black holes would need to be abundant enough to account for dark matter's gravitational effects, but not so numerous that they disrupt the formation of stars and galaxies. Additionally, their existence would leave subtle imprints on the cosmic microwave background and the distribution of matter in the universe. So far, searches for these imprints have yielded no conclusive evidence, leaving the mystery unresolved. Another complication is the wide range of possible masses for primordial black holes. If they are too small, they would have evaporated by now due to a process called Hawking radiation. If they are too large, their gravitational effects would be more noticeable, potentially conflicting with observations. This delicate balance makes it difficult to pin down their role in the cosmos. Despite these challenges, the possibility remains tantalizing. If primordial black holes do exist, they could provide a natural explanation for dark matter, bridging the gap between the early universe and the structures we see today. They could also offer insights into the nature of cosmic inflation itself, shedding light on the conditions that allowed these objects to form. As we continue to explore this connection, one thing is clear: the search for primordial black holes is not just about understanding dark matter. It's about unraveling the story of the universe's birth and evolution. Whether they exist or not, the very idea pushes us to rethink our assumptions and explore new frontiers in cosmology. With this intriguing possibility in mind, let's turn our attention to another critical phase in the universe's history: the reheating phase after inflation. How did the universe transition from a cold, empty state to the hot, dense soup of particles that set the stage for the Big Bang? Join us as we explore this pivotal moment in the cosmic inflation era. Now, let's shift our focus to a pivotal moment in the cosmic inflation era, the reheating phase. This is the dramatic transition that followed the rapid expansion of the universe, turning it from a cold, empty expanse into a hot, dense soup of particles. But how exactly did this transformation happen, and what does it tell us about the early universe? Imagine the universe at the end of inflation, vast, cold, and almost empty, with energy stored in the inflatoned field, the hypothetical force driving cosmic inflation. For the universe to become the vibrant, particle-filled place we know today, that energy had to be released. This is where reheating comes in. During this phase, the energy of the inflatoned field was transferred to particles, heating the universe and setting the stage for the hot Big Bang. The process of reheating is still shrouded in mystery. Scientists believe it involved the inflatoned field oscillating and decaying, releasing its energy in the form of particles. These particles would have collided and interacted, creating a chaotic, high-energy environment. Over time, this energy would have thermalized, meaning it spread out evenly, leading to the uniform temperature we observe in the cosmic microwave background today. But here's the puzzle: how did this energy transfer happen so efficiently? The inflatoned field had to decay in just the right way to produce the particles we see in the universe today. If it decayed too quickly, the energy might not have been distributed evenly. If it decayed too slowly, the universe might not have reached the temperatures needed for particle interactions. This fine-tuning raises questions about the nature of the inflatoned field and the mechanisms that governed its decay. Another intriguing aspect of reheating is its connection to the formation of matter. The particles created during this phase would eventually form the building blocks of everything we see: stars, galaxies, and even ourselves. Understanding reheating, then, is not just about the early universe, it's about understanding the origins of matter itself. Yet, despite its importance, reheating remains one of the least understood phases of cosmic inflation. We don't yet know the exact details of how the inflatoned field decayed or how the energy was transferred to particles. Current theories rely on complex models and simulations, but definitive evidence is still elusive. This makes reheating a key area of research, as solving its mysteries could provide crucial insights into the universe's earliest moments. As we explore this phase, one thing becomes clear: reheating was a critical turning point in the universe's history. It marked the end of inflation and the beginning of the hot Big Bang, setting the stage for the formation of all the structures we see today. Without reheating, the universe as we know it might never have existed. With this in mind, let's turn our attention to another fascinating aspect of cosmic inflation: the role of symmetry breaking. How did the early universe transition from a state of perfect symmetry to the complex, structured cosmos we observe today? Join us as we delve into this next chapter of the cosmic inflation story. Now, let's explore another fascinating piece of the cosmic inflation puzzle: the role of symmetry breaking. This concept is central to understanding how the early universe transformed from a state of perfect uniformity into the complex, structured cosmos we see today. But what exactly is symmetry breaking, and why does it matter? Picture the early universe during inflation, a place of incredible simplicity and symmetry. Everything was uniform, with no distinct structures or variations. But as the universe expanded and cooled, something remarkable happened. The symmetries that once governed the cosmos began to break, giving rise to the diversity and complexity we observe now. This process is known as symmetry breaking, and it's one of the most profound events in the universe's history. Symmetry breaking occurs when a system transitions from a highly symmetric state to one with less symmetry. Think of it like a ball sitting at the top of a hill. While the ball is at the peak, it's perfectly symmetrical. It could roll in any direction. But once it starts rolling, it chooses a specific path, breaking the symmetry. In the early universe, something similar happened. the inflattened field, which had been in a symmetric state, began to settle into a lower energy configuration, breaking the symmetry and triggering the formation of structures. But here's the mystery. Why did certain symmetries break while others remained intact? Scientists believe that the specific way symmetries broke during inflation determined the fundamental forces and particles we see today. For example, the separation of the electromagnetic force from the weak nuclear force, a process known as electroweak symmetry breaking, was a critical moment in the universe's evolution. Without it, the particles and forces that make up our world might never have existed. Another intriguing aspect is the role of symmetry breaking in the formation of cosmic structures. As the inflattened field settled into its new state, tiny quantum fluctuations were amplified, creating the seeds for galaxies, stars, and planets. These fluctuations were essentially the fingerprints of symmetry breaking, imprinted on the fabric of the universe. But why did these fluctuations take the form they did? And what determined the scale and distribution of the structures we see today? These questions remain unanswered, making symmetry breaking a key area of research in cosmology. The preservation of certain symmetries is equally puzzling. For instance, the laws of physics appear to be the same in all directions, a symmetry known as isotropy. Why did this symmetry survive while others were broken? Some theories suggest that the preservation of certain symmetries was necessary for the universe to develop in a stable and predictable way. But the exact mechanisms behind this selective symmetry breaking are still unknown. As we delve deeper into this topic, one thing becomes clear: symmetry breaking was a pivotal event in the universe's history. It shaped the fundamental forces, particles, and structures that define our cosmos. Yet, despite its importance, many questions remain. Why did symmetries break in the way they did? What determined which symmetries were preserved? And how did these processes influence the universe's evolution? With these questions in mind, let's turn our attention to another intriguing idea: the holographic principle. Could the universe during inflation be described by a holographic theory? And what would that mean for our understanding of the early cosmos? Join us as we explore this next chapter in the story of cosmic inflation. Now, let's shift our perspective to a concept that challenges the very way we think about space, time, and reality itself: the holographic principle. This idea suggests that the universe during cosmic inflation might be best understood not as a three-dimensional space, but as a two-dimensional surface encoding all the information about the cosmos. It's a radical notion, but one that could hold the key to unlocking some of the deepest mysteries of the early universe. The holographic principle draws inspiration from black hole physics, where scientists discovered that all the information about matter falling into a black hole could be encoded on its surface or event horizon. This led to the idea that our universe, too, might operate like a hologram, a lower-dimensional surface containing all the information needed to describe the higher-dimensional reality we experience. During cosmic inflation, when the universe was expanding at an unimaginable rate, this principle might have played a crucial role in shaping the cosmos. But how could this work? Imagine the early universe as a vast two-dimensional surface. Every point on this surface would contain information about the entire three-dimensional space we inhabit. As inflation stretched the universe, this information would have been imprinted on the fabric of reality, creating the seeds for galaxies, stars, and planets. The holographic principle suggests that the complexity of our universe might be encoded in a simpler, lower-dimensional framework, a concept that could revolutionize our understanding of cosmic inflation. One of the most intriguing aspects of this idea is its potential to explain the uniformity of the cosmic microwave background radiation. The holographic principle could provide a mechanism for how information about the early universe was distributed so evenly across vast distances. If the universe truly operates like a hologram, then the patterns we see in the CMB might be the result of information encoded on a two-dimensional surface during inflation. However, the holographic principle also raises profound questions. If the universe is a hologram, what does that mean for our perception of reality? Are we living in a projection of a higher dimensional reality, or is the universe fundamentally two-dimensional? And how does this principle fit with our current understanding of physics, particularly quantum mechanics and general relativity? These questions remain unanswered, making the holographic principle one of the most tantalizing mysteries of cosmic inflation. Another challenge is testing this idea. While the holographic principle offers a compelling framework, it's difficult to find direct evidence that supports it. Some scientists are exploring ways to detect subtle signatures in the cosmic microwave background or gravitational waves that could hint at a holographic universe. But for now, the principle remains a theoretical possibility, one that could reshape our understanding of the cosmos if proven true. As we ponder the holographic principle, it's clear that this idea pushes the boundaries of our imagination. It challenges us to rethink the nature of space, time, and reality itself, offering a new lens through which to view the mysteries of cosmic inflation. But with every question it answers, it raises even more, leaving us to wonder, could the universe truly be a hologram, and what would that mean for our place within it? With this mind-bending concept in mind, let's turn our attention to another profound mystery, the information paradox. Could information have been lost during cosmic inflation? And what would that mean for our understanding of the universe's origins? Join us as we explore this next chapter in the story of cosmic inflation. Now, let's venture into one of the most perplexing mysteries of cosmic inflation, the information paradox. This puzzle revolves around a fundamental question: could information about the early universe have been lost during the rapid expansion of cosmic inflation? And if so, what would that mean for our understanding of the universe's origins and the laws of physics? The information paradox first gained attention in the context of black holes. When matter falls into a black hole, it seems to vanish, taking all its information with it. This contradicts a core principle of quantum mechanics, which states that information cannot be destroyed. The paradox has puzzled physicists for decades, and now a similar question arises in the context of cosmic inflation. Could the rapid expansion of the universe have erased or scrambled information about its initial conditions? To understand this, let's revisit what cosmic inflation was like. During this era, the universe expanded faster than the speed of light, stretching space itself to unimaginable scales. This expansion could have caused regions of the universe to become so far apart that they lost contact with each other. If information about the early universe was confined to these isolated regions, it might have become inaccessible, effectively lost to us. This raises the possibility that some details about the universe's birth are forever hidden, leaving us with an incomplete picture of how everything began. But why does this matter? Information is the foundation of physics. It allows us to trace the history of the universe, predict its future, and understand the rules that govern it. If information was lost during inflation, it would challenge our current understanding of how the universe works. It could mean that some aspects of the early universe are fundamentally unknowable, leaving gaps in our knowledge that we might never fill. Some scientists argue that information isn't truly lost. It's just hidden or encoded in ways we don't yet understand. For example, the holographic principle we discussed earlier suggests that information about the universe might be stored on a two-dimensional surface, even if it appears lost in three-dimensional space. If this is true, then the information paradox might not be a paradox at all, but rather a clue pointing us toward a deeper understanding of reality. Others propose that quantum mechanics could hold the key. Quantum entanglement, a phenomenon where particles remain connected across vast distances, might have preserved information during inflation. If entangled particles were stretched across the expanding universe, they could have carried information with them, ensuring that nothing was truly lost. This idea offers hope that the information paradox might one day be resolved, but it also highlights how much we still have to learn about the quantum nature of the cosmos. The implications of the information paradox are profound. If information was lost during inflation, it could mean that our universe is just one of many possible outcomes, with some details forever beyond our reach. On the other hand, if information was preserved, it could reveal new insights into the fundamental laws of physics, helping us piece together the story of the universe's birth. As we grapple with this mystery, it's clear that the information paradox challenges us to rethink our assumptions about the universe. It forces us to confront the limits of our knowledge and consider the possibility that some truths about the cosmos might remain hidden. But it also inspires us to keep searching, to push the boundaries of science, and to uncover the secrets of the early universe. With this thought-provoking mystery in mind, let's turn our attention to another fascinating question. Could exotic particles like actions have played a role in cosmic inflation? Join us as we explore the next chapter in the story of cosmic inflation. Now, let's shift our focus to another intriguing piece of the cosmic inflation puzzle, the role of exotic particles. Among these, actions stand out as a particularly fascinating candidate. These hypothetical particles, first proposed to solve a problem in particle physics, might hold the key to understanding some of the deepest mysteries of the early universe. But what exactly are actions, and how could they have influenced cosmic inflation? Actions are theorized to be incredibly light, almost ghostly particles that interact very weakly with ordinary matter. They were originally introduced to explain why certain symmetries in the laws of physics appear to be preserved, despite predictions that they should be broken. But beyond their role in particle physics, actions could have played a crucial part in the rapid expansion of the universe during cosmic inflation. Some scientists suggest that actions, or particles like them, might have been the driving force behind the inflaton field, the mysterious energy field that powered inflation. The idea is that these exotic particles could have created the conditions necessary for inflation to occur. For example, their unique properties might have allowed them to dominate the energy density of the early universe, triggering the rapid expansion we associate with cosmic inflation. If this is true, then actions could be the missing link between the quantum world and the large-scale structure of the cosmos. But here's the catch: we have no direct evidence that actions exist. So how do we even begin to look for them? Detecting actions is no easy task. Because they interact so weakly with ordinary matter, they are incredibly difficult to observe. However, scientists have devised some ingenious experiments to try and catch a glimpse of these elusive particles. One approach involves using powerful magnetic fields to convert actions into detectable photons. Another method relies on ultra-sensitive detectors placed deep underground, shielded from cosmic rays and other background noise. While no definitive detection has been made yet, these experiments are pushing the boundaries of what we know about the universe. The mystery of actions and other exotic particles raises profound questions about the nature of reality. If they exist, they could provide a window into the quantum processes that shaped the early universe. They might also help us understand dark matter, as some theories suggest that actions could make up a significant portion of this mysterious substance. But if they don't exist, then we're left with a gap in our understanding of cosmic inflation and the forces that drove it. This brings us to the heart of the mystery. Are actions real, or are they just a theoretical construct? The answer could reshape our understanding of the universe. If actions are discovered, they could unlock new insights into the physics of the early cosmos, revealing how quantum fluctuations grew into the galaxies and structures we see today. On the other hand, if they remain undetected, it might force us to rethink our theories about cosmic inflation and the fundamental nature of matter and energy. As we continue to explore this mystery, one thing is clear: the search for exotic particles like actions is more than just a scientific endeavor. It's a journey into the unknown. It challenges us to think beyond the limits of our current knowledge and to imagine new possibilities for how the universe works. And as we push the boundaries of detection and observation, we might just uncover secrets that change our understanding of reality itself. With this in mind, let's turn our attention to another captivating mystery: how cosmic inflation might have set the direction of time in the universe. Stay with us as we unravel the next chapter in the story of cosmic inflation. Now, let's venture into one of the most profound mysteries of all, the arrow of time. Why does time move forward, and could cosmic inflation have played a role in setting this direction? This question takes us to the very heart of how we perceive the universe and its evolution. Time, as we experience it, has a clear direction from past to future. We remember the past but not the future, and processes like aging and entropy seem to move in only one direction. But why is this the case? In the laws of physics, most equations are time-symmetric, meaning they work just as well whether time moves forward or backward. So, what breaks this symmetry and gives time its arrow? One intriguing possibility is that cosmic inflation set the stage for the arrow of time. During inflation, the universe underwent an incredibly rapid expansion, stretching quantum fluctuations into the seeds of galaxies and large-scale structures. This expansion might have created a kind of initial condition for time, establishing a direction that has persisted ever since. Think of it like blowing up a balloon. Once it starts expanding, there's a clear direction to its growth. Similarly, inflation could have set the universe on a one-way path, defining the flow of time we experience today. But the mystery deepens when we consider entropy, a measure of disorder in the universe. The second law of thermodynamics tells us that entropy always increases over time, which aligns with our experience of time moving forward. Some scientists suggest that the low entropy state of the early universe created during or just after inflation might be the reason time has a direction. If the universe began in an extremely ordered, low entropy state, it would naturally evolve toward higher entropy, creating the arrow of time we observe. However, this raises another question. Why was the early universe in such a low entropy state to begin with? Some theories propose that cosmic inflation itself might have reset the entropy of the universe, creating the conditions for time to flow in one direction. If true, this would mean that inflation didn't just shape the structure of the cosmos, it also defined the very nature of time. Yet, the connection between inflation and the arrow of time remains speculative. While the idea is compelling, we lack definitive evidence to confirm it. This leaves us with a tantalizing mystery. Did cosmic inflation set the direction of time, or is there another explanation we haven't yet uncovered? As we ponder this question, it's worth noting that the arrow of time isn't just a scientific curiosity, it's fundamental to our existence. Without it, the universe as we know it wouldn't function. Stars wouldn't form, life wouldn't evolve, and the cosmos would lack the structure and complexity we see today. Understanding the origin of time's direction could reveal profound truths about the nature of reality itself. With this in mind, let's turn to another captivating mystery: the role of vacuum energy in cosmic inflation. How did this mysterious force drive the rapid expansion of the early universe, and what does it tell us about the cosmos today? Stay with us as we explore the next chapter in the story of cosmic inflation. Now, let's shift our focus to another fascinating puzzle: the role of vacuum energy in cosmic inflation. What exactly is vacuum energy, and how could it have powered the universe's explosive expansion in its earliest moments? This mystery takes us to the heart of one of the most enigmatic forces in physics, a force that might hold the key to understanding not just the past, but also the present and future of our cosmos. Vacuum energy is the energy that exists in empty space, even in the absence of matter or radiation. It's a concept that arises from quantum mechanics, where particles constantly pop in and out of existence, creating a kind of background hum of energy. During cosmic inflation, this vacuum energy is thought to have been incredibly powerful, driving the universe to expand faster than the speed of light. Imagine a cosmic engine fueled by the energy of empty space itself, pushing the universe to grow exponentially in a fraction of a second. This rapid expansion smoothed out the cosmos, creating the conditions for the universe we see today. But here's where the mystery deepens. Today, we observe something called dark energy, which is causing the universe to expand at an accelerating rate. While dark energy and vacuum energy share some similarities, they're not the same. The vacuum energy during inflation was vastly stronger than the dark energy we measure now. Why is there such a dramatic difference? If vacuum energy was so potent during inflation, why did it weaken to the relatively subtle force we call dark energy today? This discrepancy is one of the biggest unsolved questions in cosmology. One possibility is that the vacuum energy during inflation was tied to a specific field, like the inflaton field, which drove the rapid expansion. Once inflation ended, this field might have decayed or transformed, leaving behind a much weaker form of energy, dark energy. Think of it like a roaring fire that burns brightly for a short time, then settles into glowing embers. The fire represents the intense vacuum energy of inflation, while the embers symbolize the dark energy we observe today. But why this transition happened and what caused it remains a mystery. Another intriguing idea is that vacuum energy and dark energy are fundamentally different phenomena. Perhaps the vacuum energy of inflation was a unique, one-time event, while dark energy is a constant feature of the universe. This raises even more questions. If they're different, what connects them, if anything? And why does dark energy exist at all? These questions highlight the complexity of understanding the forces that shape our universe. The mystery of vacuum energy isn't just about the past, it's also about the future. If dark energy continues to accelerate the universe's expansion, what does that mean for the ultimate fate of the cosmos? Could dark energy evolve over time, or is it a fixed constant? These questions remind us that the story of cosmic inflation isn't just a tale of the distant past, it's a narrative that continues to unfold, shaping the universe we live in today. As we explore these ideas, it's clear that vacuum energy and dark energy are two sides of the same cosmic coin, yet they remain shrouded in mystery. What drove the universe's explosive beginning, and what drives its expansion now? The answers to these questions could reveal profound truths about the nature of reality itself. With that in mind, let's turn to the final chapter in our journey, the future of inflation research. What new discoveries might await us as we continue to probe the mysteries of the early universe? Stay with us as we explore the cutting edge of cosmic exploration. Now, as we step into the final frontier of our exploration, let's turn our gaze toward the future of inflation research. What lies ahead in our quest to unravel the secrets of the early universe? The mysteries of cosmic inflation are far from solved, but scientists are pushing the boundaries of technology and theory to uncover answers that could reshape our understanding of reality itself. One of the most exciting developments in this field is the next generation of telescopes and observatories designed to probe the cosmic microwave background, or CMB, with unprecedented precision. Projects like the Simons Observatory and the upcoming LightBird mission aim to detect faint imprints left by inflation, tiny ripples in spacetime known as primordial gravitational waves. These waves, if found, would be a smoking gun for cosmic inflation, offering direct evidence of the universe's explosive beginnings, but the challenge is immense. These signals are incredibly faint, buried beneath layers of cosmic noise. Detecting them would be like trying to hear a whisper in a roaring storm. Yet the potential payoff is enormous, a glimpse into the universe's first moments. Another promising avenue of research involves particle accelerators like the Large Hadron Collider. While these machines are typically associated with discovering new particles, they could also shed light on the physics of inflation. By recreating the extreme conditions of the early universe, scientists hope to uncover clues about the inflaton field, the hypothetical energy field that drove inflation. Could this field be connected to particles we've yet to discover, or might it reveal new symmetries or forces that govern the universe's infancy? These experiments could bridge the gap between cosmology and particle physics, offering a unified picture of the cosmos. Meanwhile, theoretical physicists are exploring bold new ideas such as string theory and quantum gravity to explain the mechanisms behind inflation. These theories attempt to reconcile the bizarre rules of quantum mechanics with the vast scales of the cosmos, offering potential insights into how inflation began and why it ended. Could inflation be a natural consequence of a deeper, more fundamental theory? Or is it just one piece of a larger cosmic puzzle? These questions drive some of the most cutting-edge research in physics today. But perhaps the most tantalizing prospect is the possibility of entirely new discoveries, ones we can't yet predict. History has shown that every time we probe the universe with new tools, we uncover phenomena that challenge our assumptions. What if inflation isn't the whole story? Could there be other forces or fields at play in the early universe waiting to be discovered? The future of inflation research isn't just about confirming what we already suspect, it's about being open to the unexpected. As we look ahead, one thing is certain: the mysteries of cosmic inflation are far from over. Each new experiment, each new theory, brings us closer to understanding the universe's origins. But with every answer comes new questions, reminding us that the cosmos is a place of endless wonder. What will the next decade of research reveal? Will we finally detect primordial gravitational waves? Will we uncover the nature of the inflaton field? Or will we stumble upon something entirely unexpected? The future of inflation research holds the promise of discovery and the thrill of the unknown. And with that, we've reached the end of our journey through the 25 mysteries of the cosmic inflation era. From the universe's explosive beginnings to the forces shaping its future, these questions remind us of how much we've learned and how much remains to be discovered. The story of cosmic inflation is far from finished, and the next chapter is waiting to be written. What mysteries will we uncover next? Only time and the relentless curiosity of science will tell. As we bring our exploration of the 25 mysteries of the cosmic inflation era to a close, it's worth reflecting on just how far we've come and how much further we have to go. From the rapid expansion of the early universe to the enigmatic inflaton field, these mysteries have not only shaped our understanding of the cosmos, but also challenged us to think beyond the limits of our current knowledge. Each question we've explored, whether it's the horizon problem, the nature of dark energy, or the tantalizing possibility of a multiverse, reminds us that the universe is far more complex and wondrous than we could have imagined. These mysteries aren't just academic puzzles, they're windows into the very fabric of reality. They push us to develop new technologies, refine our theories, and question our assumptions. They remind us that science is a journey, not a destination, a continuous quest to uncover the truths hidden in the vast expanse of space and time. And while we've made incredible strides, the answers we found often lead to even deeper questions, keeping the flame of curiosity alive. So, what's next? Will we one day detect the elusive primordial gravitational waves, confirming the story of cosmic inflation? Will we uncover the secrets of the inflaton field or discover new forces that shaped the early universe? Or will we stumble upon something entirely unexpected, rewriting the cosmic narrative once again? The future of inflation research is as unpredictable as the universe itself, and that's what makes it so thrilling. As we wrap up, I want to leave you with this thought. The mysteries of the cosmic inflation era aren't just for scientists to solve, they're for all of us to ponder. They invite us to look up at the night sky and wonder about the forces that shaped our existence. They remind us that the universe is a place of endless discovery, waiting for curious minds to explore its secrets. If you've enjoyed this journey through the mysteries of cosmic inflation, don't forget to share your thoughts in the comments below. What mystery fascinates you the most? What do you think the next big discovery will be? And if you're hungry for more space mysteries, be sure to hit that subscribe button and ring the notification bell so you never miss an update. The universe is full of wonders, and together we'll keep exploring them one mystery at a time.